In this newest video in our series on doing things with geometric algebra, we will use geometric algebra to solve a nice multiple tangency problem. The problem statement is as follows. We have a rectangle, two small congruent centers, or circles rather, and a line that is tangent all three circles starting from one corner. The problem is one that I found on a very nice website, or a very nice channel on YouTube, rather. And it is Anmol, the math sailor. He attributes this problem to quite a wonderful website, Mirangu.com, and I hope you'll check that out. It has almost every day, or on its X account, another really beautiful problem. So, thanks to Anmol, thanks to Mirangu, and now back to our solution. But I will link this video in the upper right hand corner and also in the video description. I will also link Mirangu's site in the video description. So, back to our solution of the problem. First, the PDF goes through some ideas that we'll use. I've presented a lot of these in some detail for people who might be new to geometric algebra, but we'll just go through the key ones here. One is that in geometric algebra, we can very easily express the reflection of one vector with respect to another. For example, here Q prime is a reflection of Q with respect to T, and we can form that or effect that reflection by multiplying Q on both sides by the unit vector T, just as shown here. So that's all very convenient. Another key idea here is that the products of unit vectors in geometric algebra operate or function as rotation operators, and we'll show that with reference to this diagram. Here we have two unit vectors. Their geometric product is a rotation operator. So here we have the angle between P hat and Q hat in this sense, and we'll define this sense as the sense of the unit bivector I of this plane. So if we multiply V on the right by P hat Q hat, what we get is as we rotate V, the original V, by the angle theta that's between P hat and Q hat, and in the same sense. If we now multiply V P hat Q hat again by P hat Q hat, we get an additional rotation by theta. We can write the same operation in exponential form as V times e to the I, the same I here, times 2 theta, twice this angle. So this is often very convenient to use either this form or the exponential. Here we will end up using both. So, on with our solution. First we want to analyze a problem based on an initial formulation. So these operations usually kind of develop organically in combination. We look at something, analyze it a bit, come up with a formulation initially, modify the formulation as we go through it and do more analysis. Here, this is our initial formulation based upon an initial examination. What we can see here is that this line that is tangent all three circles is a reflection of this side with respect to the line that goes from this corner through the center of this circle. But at the same time, this line that is tangent all three circles is the reflection of this side of the rectangle with respect to this line that goes through these centers and through that corner. Another thing we see here is that by doing just basic similar triangles, we can see that this length divided by this length is equal to that length divided by that length. And if we write that down in terms of A, B, and R, and do a little simplification, we come up with this equation which we'll use later. So our strategy is we have one equation here that from which we could find r in terms of a and b, but also we can use these reflections here to come up with an independent equation for r in terms of a and b. So we'll use these reflections to come up with one equation for r in terms of a and b, substitute the r from the reflection equations into this one from similar triangles, and having eliminated r in that way, we will work out what b is in terms of a. So that is our strategy, and based upon that strategy, now we're going to refine our formulation and come up with a final formulation here. We defined the unit vectors a hat and a hat I, which is rotation of a hat by 90 degrees in the sense of rotation of I, and we can formulate this line of reflection, or this vector reflection, in terms, or I'm sorry, I should phrase it differently. We can see here that S hat is the reflection of A hat with respect to this vector, which we've formulated in terms of A and R, and also S hat is reflection of A hat I with respect to W, this vector, which we've also expressed in terms of A and B. So now we can express both W and Z in terms of A, R, and B, and we also have the reflection equation. This Z hat, A hat, Z hat is reflection of A hat with respect to Z, which gives S hat, but S hat is also the reflection of A hat I with respect to W, so the, S is also W hat, A hat I times W hat. So that is our reflection equation. Both sides here are equal to S hat. We also show here the angle phi, which we will not use in the analysis, but we will use later for our convenience during our discussions. So at this point we've defined W, we have defined Z, we have another independent equation, the one that we saw, that we got earlier from the similar triangles. So now we can go ahead, find an equation for r, or an expression for r in terms of a and b from this equation, substitute that r into here, and then get b in terms of a. Now we will find, or excuse me, we will use two different ways of getting an expression for r in terms of a and b out of this equation. One is a bit gnarly. I won't go into it here, but it works perfectly well. You can follow it in the PDF of the solution. I want to show instead here the way that uses the rotations, or we transform equation 5.2, which was this thing, into a rotation. And then it becomes really quite simple and not at all gnarly. So one thing that we recognize as we go through these transformations, or one thing we keep in mind as we get an idea of what to do here, is if we multiply both sides by on the left by W hat, here we get W hat, Z hat, A hat, Z. W hat here is 1. Same thing happens on the right hand side. So we end up with W hat, Z hat, A hat, Z hat, W hat times, or equal to 1 times A hat I times 1. So we get this. But something that was shown earlier but we didn't go into in this video is W hat, Z hat, A hat can also be written as A hat times Z hat, W hat. The order of these reverses. So now we have A hat, Z hat, W hat times Z hat, W hat is A hat I. what this product is, going back to our earlier diagram, would be a rotation by twice this angle. So we'll go back here quickly, pardon me. Overshot there, pardon. So when we rotate a hat by twice the angle between z hat and w hat, and we'll call that angle phi, which we saw earlier, if we rotate a hat by twice phi, we get a hat rotated by pi over 2, so by 90 degrees. So following that, pi over 2 is the double of phi, so phi must be pi over 4. And again, this is easier to follow in the PDF. So phi is pi over 4, and we equate the expansion of z hat w hat to the trigonometric form, and we see that z hat w hat is cosine phi plus I sine phi. For the angle phi, cosine phi and sine phi are equal, of course. So if we use another idea that was presented earlier but which we didn't go into here, we can equate cosine phi to sine phi in terms of the inner and outer products of z hat and w hat. Now that looks gnarly, but all this is writing here. There's no real work involved up to this point. Finally now, after just doing simple rewritings, which doesn't require any work at all, and not a whole lot of thinking either for that matter, finally now we can write down here or make substitutions for z and w, and now finally we actually have to do just a little bit of work. And what we come up with here is this nice simple equation for r in terms of a and b. So now we have an expression for r, and we plug that into the equation that related r in terms of a and b that we got from the similar triangles. And when we make that substitution, eliminate r, we get b is equal to 2a over 3, or b over a is 2/3, and r is a over 8. Now, we can check that quite easily via a geometric algebra construction, and that's done here. Here, a is 12, and b we can see is 8. So b is indeed 2/3 of a. Also, r is 1.5, 1.5, a is 12, so a is indeed, or r is indeed a over 8. So I hope that you'll check out the PDF. I also hope that you'll check out our LinkedIn group, which I present the link for here in the PDF, and we'll also link in the video description. I hope that you will let me know of any corrections or any improvements on this video that you might see, and thank you for